All right, let's start talking about electrons and orbitals. So we learned back in Unit 3 about Schrödinger and his work developing quantum mechanics. He developed these whole series of equations that identify these three-dimensional shapes where electrons are likely to exist based on how much energy those electrons should have, and he called these 3D regions orbitals. Those orbitals are what we're going to be dealing with here a lot throughout this lecture. So, before we can really talk about orbitals, though, we need to kind of revisit the idea of energy levels. Bohr came up with these idea of energy levels, distinct amounts of energy based on where the electron's located in relationship to the nucleus. The closer it is, the lower the energy level. Well, these energy levels we give the variable n. They correspond to periods on the periodic table. In other words, they correspond to rows on the periodic table. So row 1 is energy level 1, 2, 3, 4, etc. The higher your energy level, the higher the energy. That kind of should go without saying. It's exactly what it sounds like. Now, here's where it gets a little bit more interesting. Every energy level also has sublevels. It has the same number of sublevels as the energy level itself. So energy level 1 has one sublevel. Energy level 2 has two sublevels. 3 has 3, 4 has 4, so on and so on and so forth. Right now, the highest energy level elements that we have are at 7. Nothing is beyond that yet that we've discovered to be stable, but in theory, if you had energy level 100, it would have 100 sublevels. It's pretty straightforward. You're going to see this chart a few times as we go through this video. It helps you relate energy levels to sublevels, to orbitals, which we'll get to in a second, and electrons per sublevel. We'll get to that in a second. But right now, we're just kind of looking at this portion of it right here. Energy level 1 has one sublevel, energy level 2 has two sublevels, 3 is 3, and 4 has 4. In other words, for any energy level n, there can be at most n sublevels. So now that we're talking about sublevels, let's really get into some more detail with them. There are, for now, only 4 sublevels that you're going to ever have to really deal with. S, P, D, and F. S is the first one, P is the second one, D is the third one, F is the fourth one. Always. You always have to have the one before you can get to the next one. So every energy level has an S. Before you can have a P, you have to fill the S. Then you can go to P. Then you can go to D. Then you can go to F. It's like the idea of a pyramid. You can't just build the top capstone of the pyramid before you have all the foundations down there. You can't have an F sublevel until you have a D. Well, you can't have a D until you have a P. You can't have a P until you have an S. And that's at increasing energy levels required to get into that sublevel. S is the most stable. It requires the least amount of energy for an electron to be there. F is the highest for now. It requires the most energy to be there. Now, these sublevels are made up of orbitals, and remember that's what Schrödinger described as these three-dimensional areas where an electron is likely to be found. Also, remember again, as we go through these sublevels, for every energy level, you have that many sublevels. So energy level 1 only has one sublevel, an S. Energy level 2 has two sublevels, S and then a P. Energy level 3 would have 3 sublevels, S, P, and then a D, etc., so on and so forth. So what do these three-dimensional regions look like according to Schrödinger? We've used computers to model them, so they're a little bit easier and clearer to see. The first sublevel is a sphere. It's why it's one of the reasons it's called S. And it has a single orbital in it. There's only one way that you can kind of orient this sphere. You could rotate it whatever direction you want. It's still going to just be a single sphere. So every S sublevel has exactly one orbitals where electrons can live. When you jump up to P, we call that the dumbbell shape, okay? Because it looks, kind of like a dumbbell or a dumbbell in a gym. And you could orient that dumbbell 3 different ways. You could have it lie along the x-axis, you could have it lie along the y-axis, or you could have it lie along the z-axis. 3 different orientations mean you can have 3 distinct, different orbitals. So S has 1, P has 3. Moving up to D, we call that the cloverleaf shape or the four-lobe shape. And it has 5 orbitals. It could be arranged in 5 different distinct and unique ways, including this weird spinny one. Don't worry about it too much. Just know, again, S has 1, P has 3, D has 5 orbitals. And lastly, F is the super complex shape. We'll never ask you what shape F exists in, but know that it can be oriented in 7 different ways. Hopefully you've seen that pattern, 1, 3, 5, 7. If there was a hypothetical G sublevel that came after F, hopefully you could kind of look at the pattern, 1, 3, 5, 7. G would have 9, and so on and so on and so on. There is not a 9 as far as elements that currently exist. There's only 4, and even still, we're not going to be dealing with F very often. You do need to know it, but pretty much you'll be sticking within the S, P's, and the D's. All right, back to that chart again. We have energy levels relating to sublevels. For every energy level in, there's exactly in sublevels, 1, 1, 2, 2, 3, 3, 4, 4, go on and so forth. But now we also know that for any energy level in, there is in squared orbitals. And you could just memorize that if you want to, or you can actually work it out. For energy level in, or energy level 1, there is 1 sublevel. You have to start with S, so the only sublevel on energy level 1 is S. And we just learned based on the shapes that it has exactly 1 orbital. Since the only sublevel it has is S, and it only has 1 orbital, we know that in all of energy level 1, there is a single orbital. Now let's look at 2. Energy level 2 could have 2 different sublevels. You have to start with S, but since it can have 2, it can also have a P sublevel. We learned based on those last couple slides, S has 1 orbital, P can have 3. Therefore, on energy level 2, I can have a total of 4 orbitals, in other words, 2 squared. Energy level 3 has 3 sublevels, S, P, and then you get to add the D sublevel. S has 1, P has 3, D has 5, for a total of 9. 4, 4, S, P, D, F, 1, 3, 5, and 7 from the F. 1 plus 3 plus 5 is 9. Excuse me, math is hard. 9 plus 7 is 16. So you got your n squared. We'll deal with these last 2 columns here in just a second. But for any energy level, there is at most n squared orbitals. Okay, according to Schrodinger's calculations and some rules that we're going to talk about here in the next day or so, we know for a fact that every single orbital can have at most 2 electrons. Does not matter what energy level, does not matter what sublevel, every single orbital can hold 2 electrons. Well, what that tells us is that since we know that S has 1 orbital, and we know each orbital can hold 2 electrons, we know that S sublevels, regardless of whether they're energy level 1, 2, 3, 4, all the way up to infinity, every single S sublevel can only hold 2 electrons. P could have up to 3 orbitals. Each orbital can hold 2, so every single P, whether it's on 2, 3, 4, 5, can hold 6. Every D has 5 orbitals, so every D sublevel has 10 electrons at most. It could have less, and we'll talk about how we know if it has more or less in the next day or so. But know that at most, you can have 10 electrons in a D sublevel. Last but not least, F has 7 orbitals, so any F can have at most 14. Which brings us to our fully completed chart. We know that for every energy level in, there is n sublevels that we can describe as S's, P's, D's, or F's, depending on energy level and how the progression has gone. We know based on those sublevel shapes and orientations, the number of orbitals. Every S has 1, every P has 3, every D has 5, every F has 7. From that, we could calculate the total number of orbitals in every single energy level as n squared. So 1 has 1, 2 has 4, 3 has 9, 4 has 16. And now we know that for every orbital, you can have 2 electrons. Every s can have 2. Every p can have 6. Every d can have 10. Every f can have 14, which means not only can you count total number of orbitals, you could also potentially count total number of electrons per energy level maximum. And that's really important. I'm saying maximum. You could have less depending on the situation. We'll deal with that later. Okay. Now you could memorize that it's really just 2 times n squared, because 2 electrons per orbital. Or like this table has it written out, you could break the whole thing down into orbitals, do 2 per orbital, add it all back up together to get your totals. It's kind of up to you. You just need to be able to very quickly be able to go from energy level to potential total energy, electrons, and everywhere in between. So make sure you can break it down. Make sure you kind of understand how all these sublevels kind of work out and break down. If you do need a little bit more guidance of how we remember how many electrons are in each orbital, we can break the periodic down into something called blocks. So we have an s block, a p block, a d block, and the f block. The s block is the first 2 columns of your periodic table, the hydrogen and the or group 1, essentially group 1 and group 2, with the exception of helium. It kind of moves over to join the hydrogen side. That's the s block. If your element is in that section, you're going to end with an s orbital. But everything in there is an s orbital. So whether we're here, that's going to be 2s, there's 1s, 3s, 4s, 5s, 6s, 7s. But they're all s's. Everything there is an s orbital. Jumping to the far right side of your periodic table, we have the p block. Everything there is going to be a p sublevel. Now, we kind of should understand at this point, but my p block always starts at 2. For a pretty simple reason. Energy level 1 can have 1 sublevel, and that 1 sublevel has to be an s. It has to be 1s. There is no such thing as 1p. The first p sublevel starts at 2. So 2p, 3p, 4p, 5p, and 6p. And there's a 7p now that exists with recently discovered elements. But, you know, it's the idea that you could keep going to infinity if you really, really want to. This middle section we call the D block. There are 10 columns in the D block to match the 10 electrons in the D block. Notice how there's 2 columns for the S and 6 for the P. It's kind of a way to help you remember. The D block's in the middle. We'll talk about electron and the orders, but just know that's the 3D, then 4D, then 5D, then 6D, 7D, etc. Okay, because remember, you have to have enough sublevels to get up to the D. You have to have an S, then you have to have a P before you have a D. Okay, so S, P, D, which means the first time you'd ever see a D would be on the 3rd energy level. Last but not least, there's the F block. It's the 2 rows on the bottom of the periodic table. Like I said, we're never going to really deal with these elements, but do know they are there. We call it the F block. Which brings us to the first of the 3 rules for how we do something called orbitals or filling orders. Aufbau's principle is this idea that says, okay, electrons will fill energy levels starting with the easiest to get into, the lowest energy requirement, and will then fill from lowest to highest, which means essentially electrons will always fill energy level 1 before they move on to 2. That's the general gist with Aufbau's principle. Energy level has one sublevel, an S, so together we call it 1s, which means before I can move on to energy level 2, I have to finish filling up 1s. Once 1s is full, then I move on to the next one. Well, the next one up is going to be 2s, and then 2p. Then you can move on to energy level 3, 3s, 3d, 3p, 3p, 3d, excuse me. Then you move on to energy level 4, 4s, 4p, 4d, 4f. So you would think, just based on this order, this is essentially would be the order that would come. Then next would be 5s, and then 5p, and then 5d, and then 5f, and then up to 6, so on and so on and so on. The problem is, for reasons that you don't really have to worry about, the energy requirement to get into some sublevels are easier to get into than other sublevels. Okay, and I know that's a little confusing, but we're going to talk about a way for you to kind of help see that here in just a second. The actual real filling order would be 1s, 2s, 2p, then 3s, which is good, that's normal, and then 3p, which is normal. But then before you get to 3d, you actually have to fill 4s. So you jump up to energy level 4s and then back down to 3d. For the simple reason is it's easier for an electron to fit into 4s than it is for 3d. 4s is a really simple, remember it's just a sphere, whereas 3d is that crazy complicated lobes with the one that's spinning, so it's a little bit more complicated, and since it's more complicated, it actually requires more energy. It's just to the point where it's easier to get into a higher energy level but simpler orbital than it is to get into a lower energy level but more complex orbital. Don't memorize this. You can if you want, but like I said, we're gonna talk about a way to kind of help you read the periodic table like a book in order to get this filling order out. Now, this is what a periodic table should really look like. I know the one in the board in the classroom or in your textbooks or on the internet, they're gonna look the same. They don't look like this, right? They have that extra 2 rows on the bottom. Well, those 2 rows on the bottom are that F block right there. But in the real world, this is where they should be. They should be stuck between the first 2 columns and the 10 columns in the middle. Now, the reason they pull it out, it's for a pretty simple publisher reason. They need it to fit on one piece of paper. So they pull out this F block, they stick it underneath, and they just kind of say, hey, don't forget that these 2 rows are there. So what you're going to have to be able to do is essentially read the periodic table like a book. We read books left to right, top to bottom. Right? So you can read, we know that. So you're going to read the periodic table exactly like you would a book. You're going to start in the top left, and you're going to read left to right. Well, the first energy level is 1. I'm starting in an S. Read across, read across, read across, read across. Energy level 1's done. Remember that helium really kind of fits in the puzzle right there. We'll talk about why helium's over there when we get to Unit 5. So we have 1s. I hit the end of the line. What do you do when you read a book? Well, you just go to the next line down. Well, the next line down is going to be energy level 2. So 2. And I'm starting in the S block, so my next energy level is 2s. I read across, read across, read across, read across. Oh, hey, look, I hit a P sublevel, which tells me the next one that's going to fill up is 2p. And I read that through the line. Oh, hey, I hit the end of my line, go to the next one down. Oh, the next one is energy level 3, and it's a 3s. I read across, read across, read across, read across, read across, and then I hit a 3p. So far, so good, nothing too crazy. Here's where it gets interesting. I hit the end of my line. I go down to my next line. The next energy level is 4. That's what the book says. And it's a 4s. Just like that. Now I read across, read across, read across, read across, and I hit my first D block. And it's the first time I've hit that D row throughout this entire process. Now, remember, every energy level has that many sublevels, which means the first time I should have hit the D sublevel was back on energy level 3, right? 3s, 3p, 3d. Energy level 3 has 3 sublevels. It has to have 3 sublevels. So the first time I hit a D sublevel, it gets designated with the 3, because that's the first one it should have been. I read across, read across, read across, read across. Now I'm back to the P block. Well, I've already had a 3P, so the next one up has to be 4P. Read across, read across, read across, hit the end of the line, drop down to the bottom. Now I'm back to energy level 5. Next comes 5S. Read across, read across, read across, read across, read across. Oh, hey, it's D again. The last D I used was 3, which means the next D I'm going to have is 4. So notice how it's still kind of sequential, but you have to fill from lowest to highest. So 4D, up, I'm at a P. Well, I've already used 4P, so the next one up has to be 5P. Keep going, keep going, keep going. Next one is going to be 6S. Read across. Oh, hey, now I've finally hit the F sublevel. Remember, the first time I should have hit the F sublevel was back in energy level 4. S, P, D, F. Fourth sublevel should have been on the 4th energy level. So because that's when it should have popped up, that's what we give. That's the energy level number that we give it, 4F. Read across, read across, read across, read across. Now I hit the D block again. The last D I used was 4, which means this one's going to be 5. So on and so on and so forth. 6P. So hopefully you've kind of seen the pattern at this point. For every D, you look at the energy level row it's on, and you have to subtract 1. That just shifts it up to where it should correctly be, but due to the way we've designed the periodic table, that's just not where it sits. For sublevel F, if you ever do have to deal with it, it's going to be -2 from whatever row it's on. Okay, remember, this is how it deals with energy levels and the complexity and the energy requirements that it takes to get into it. Okay, so what this is saying is that it's harder to get into 4F than it is to get into any of those previous sublevels. That's all this is telling you. The 4F sublevel is so complicated, the electron would rather go somewhere that is just simpler for it to go. Here's another kind of visual representation for those electron configurations, those energy levels. Remember, you read the periodic table like a book. Left to right, top to bottom. You're going to get a lot of practice doing this, so don't fret if you're kind of struggling with it at first. It's weird. We're not going to lie to you. It is very, very strange. You will get used to it, but you are going to have to practice it. Okay. Okay, so we've talked about Aufbau's filling principle or Aufbau's rule, this idea that you fill from low to high. There are 2 other rules that determine how electrons fill up orbitals and fill up energy levels. The first one is going to be Hund's rule. So the idea behind Hund's rule is that when you have orbitals of equal energy, so let's say we had 3 orbitals, and they're all 3p, so P has 1, 2, 3 orbitals, so we would have 3 lines. We'll talk about how we draw orbitals here in just a little bit. What Hund's rule says is that these electrons are going to fill these orbitals one at a time before going back and starting to partner up. We also call this rule the school bus rule for a pretty obvious reason. It helps you remember because, hey, if you're getting on a school bus, are you going to try to take a seat that already has someone there who's kind of spread out and made it their own? Or are you going to take your own seat where you can now spread out all by yourself? Most of the time, you're going to want to take your own seat on the bus. So electrons are the same way. They're going to choose their own orbital that they can be all alone in before they're forced to have to sit with someone else, to have to be forced to partner up. So if I had 3 orbitals, this would be wrong. You cannot do that. These extra electrons would have to spread out first before going back and partnering up. That's what Hund's rule says. The third rule, is Pauli's exclusion principle. All it says is that when we're drawing electrons, we have to be able to tell them apart. We tell them apart by drawing the arrows in 2 different directions, one up and one down. You saw me do it up there with the Hund's rule example. I drew up arrows first, down arrows next. You can do down arrows first if you want to and then go back and do up arrows. It really doesn't matter as long as every orbital has two different direction arrows. We say that these electrons have something called opposite spin. It's pretty arbitrary which one is up and down. We literally just use it to differentiate the two electrons that are existing within the same orbital. So those are all three rules: Aufbaus, Huns, and Pauli's. We're now going to start using those rules to show something called orbital spin diagrams. We're going to start drawing all these electrons that are in our atom. So when we start drawing these diagrams, first we need to figure out essentially how much space do we need. So we're going to draw lines and boxes for every orbital and every energy level, remembering that S has 1, P has 3, D has 5, and F has 7. Okay? Then we figure out how many electrons that atom has. Because we're talking about atoms, that implies that the atom is neutral, which means it has the same number of electrons as it has protons. So if we look at chlorine, chlorine has 17 protons. So if we assume it's neutral, that tells me that it has 17 electrons, which means when I draw my spin diagrams and I represent my electrons with arrows, I'm going to have 17 arrows. Now, based on Aufbau's rule, I start at energy level 1, and I start at 1s, has one sublevel. That's everything that can fit into 1s, so then we can go on to 2s, then 2p. Remember, it's a p, has 3 orbitals, so we're going to have 3 lines. The s's have 1 orbital, so s's have 1 line. After 2p comes 3s, 3p, 4s, 3d has 5 because d's have 5. After D is 4p, 2, 3. And I think that's enough for right now. It seems like a lot of arrows, a lot of boxes, but maybe we need more. Maybe you don't need as many. We'll talk about a little shortcut way here in just a second. But we fill the orbitals, or the filling order, out to 4p. We've drawn boxes or lines to represent all those different orbitals in all those different sublevels in all those energy levels. Okay, so we have 17 electrons, we have 17 arrows. We start filling at the lowest energy level, which means 1s. So I'm going to do my 1 up arrow, 1 down arrow. Then I'm going to move to 2s, 1 up, 1 down. Then I'm going to move to 2p. Remember Huns rule, up, up, up. Then I go back and I start partnering. Now remember, I need to use a total of 17 arrows. I've used 2, 4, 10, so I have 7 more I got to use, so I got to keep going. 1 up, 1 down, that's 12. 1 up, 1 up, 1 up makes 15. 17 minus 15 is 2, so I have 2 more arrows left. 1 down, 1 down. That last orbital only has 1 electron in it, and that's okay. They don't have to be filled. The only requirement is that before they're filled, or before you move on, they have to be full. So we didn't need to go all the way to 4s, 3d, 4p. If you happen to overshoot, like we did here, and you just leave them all blank, that's fine. If you want to go in and erase them, you can do that too. But that would be considered a complete orbital spin diagram for chlorine. Here's another couple. We're gonna do one of these, and then I'll let the other 2 pop up. But let's do aluminum, Al. So we know that neutral aluminum has 13 protons, which means it's going to have 13 electrons, which means I need 13 arrows. And same way, I'm just going to start at 1s. 1s, 2s, 2p. Now, before I keep going, you can just get a lot of practice doing this filling order over and over and over and over and over until it's basically just drilled into your head so much you'll never forget it. But if you don't want to always have to be guessing at how far you have to go, there is a short way to kind of see, according to the periodic table, how far you need to fill to. Let's take a second and look at your periodic table. Find aluminum, number 13, right there under boron next to silicon. And ask yourself, what energy level is that in? Well, when I look at the periodic table, it's in energy level 3. So once you know the energy level, you can figure out, hey, what block is this in? Well, aluminum is in the P block. So I'm going to end at 3P because that's where my element is. It's in the 3P section. So I'm going to fill all the way up to 3P. That's what I'm going to end at. I know I need at least 3P to get there. Okay? Now I can start filling in my arrows according to my Aufbau's rule and Hund's rule and Pauli's exclusion rule. One up, one down, one up, one up, one up, one down, one down, one down. I've used 10 so far. There's 12, and there's 13. Sure enough, I end with 3P. So you can use the periodic table to kind of give you a guide to how far you're going to have to fill. If you pick something that's down in 6S, like cesium or barium, CS or Ba, you're going to have to fill all of 1S, all of 2S, all of 2P, all of 3S, all of 3P, all of 4S, all of 3D, all of 4P, 5S, 4D, 5P, and you're going to have to get all the way down to 6S. You're going to have to show all of those sublevels, you're going to have to show all those orbitals, but if you figure out where your element is on the periodic table, it can give you a kind of hint or a guide to how far you're going to have to go in that Aufbau filling order that we described earlier. So go ahead and take a second, pause the video here, work through oxygen, work through bromine, see if you can figure out the correct orbital spin diagram. We'll let it go for a few more seconds, and then the answers are going to pop up on the screen. So go ahead and pause it here to give you some time to work. All right, so here are your completed orbital spin diagrams for oxygen and bromine. Oxygen has 8 electrons, so should have 8 arrows, fills up to the 2p sublevel. Bromine fills 35 arrows all the way up to that 4p sublevel. Make sure you're very clearly showing all the orbitals, make sure you're clearly showing up and down arrows, and that you're not overfilling or underfilling and filling according to Pauli's exclusion principle. You need to have an up and a down for every filled orbital. So real quick review, Aufbau's principle says that electrons fill energy levels and orbitals from the lowest to the highest, starting at 1s, filling like you're reading the periodic table like a book. If you're still having trouble seeing that, please come see us. We will walk you through it together, and we'll make sure that you can replicate it on an exam. Hund's rule, electrons enter orbitals of equal energy one at a time to minimize repulsion, up, 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 down, 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 or if it's D, up, 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 then you go back and start partnering them up to downs. Lastly, Pauli's exclusion principle, every orbital can hold 2 electrons, but those 2 electrons need to have opposite spins. In other words, one up and then one down. Make sure you have a good understanding of these 3 rules. Another way we're going to test you on whether or not you understand these rules is might give you some examples and ask you to identify which rule is broken. So if we look at that first section in the top left, number 1, well, I didn't fill that energy level before I moved on, which means I violated Aufbau. If I look down, well, I filled 1 before moving on to 2, I filled 2 before moving on to 3, but oh look, I've partnered up those electrons already before I spread them all out, which means that second example is a violation of Hund's rule. That should be up and then another up in the orbital next to it. That third one should still be empty. Looking at the next one down, I filled correctly before I got to that top energy level, so we're good on Aufbau's. I've spread out like I should with Huns, so that's okay. They're all up-down arrows in any of the filled orbitals, so this is actually no violations. They're all good. It's perfectly followed. In fact, maybe you can guess what element that is. If it has 7 arrows, you should be able to tell me which element has 7 electrons when it's neutral. Looking at the bottom one, bottom left, I have 2 up arrows, another 2 up arrows. That's a violation of Pauli's exclusion principle. Okay, I'm going to let you try to do all the ones on your right on your own. I'm going to go ahead and pause the video here, see if you can identify the if any violations are occurring on the particular other side. Here are the correct answers. Top one violates Huns. The next one down violates Pauli because of that circled section that has 2 up arrows. The third one down is perfectly good. And the last one is an Aufbau filling issue. You didn't fill the lower level before you moved on. Again, if you're having trouble kind of seeing how these rules work, or you're having troubles remembering how to do the filling order, please come see us. We will work with you on these problems. It is vital that you have these understanding so that you can get through the filling order, so you can get through the spin diagrams, and so that we can start showing you the shortcuts so you don't have to draw 35, 40, 55 arrows. We'll start showing you some shortcuts here in the next day or so.